Number 12 talks about the 3 machines used to produce a large quantity of parts at a factory. And we have machine A, machine B, and machine C. And it says the historical records indicate that 10% of the parts made at A are defective, 30% at B, and 40% at C. And we're supposed to randomly select a part that was produced at the factory. So I'm going to make a, a tree diagram for this. So I'm just going to create myself some space where first I'm selecting a part produced at the factory. So I don't know which machine it is. That's what I'm going to first branch it off into. We have machine A, we have machine B, we have machine C. And I know that 60% come from A, 30% come from B, leaving 10% from C. And either, when you make a part, it's either going to be defective or it's not. That's going to be true for all these different machines. So I'm just going to go ahead and duplicate those because I know I'm going to need them. Whoa, I'm not going to do that though. Okay, so according to their records, 10% produced by A will be defective, which leaves 90% to be just fine. 30% are defective at machine B, so 70% are fine. And 40% of the parts from machine C are defective, leaving 60% not to be defective. We're going to randomly select a part produced at this factory, and we're going to find the probability that the part is defective. Now, there are 3 different branches that end with a defective part. So we just want to be able to consider any of these or any of them possibly happening. So I'm going to put the probability of a defective part could be machine A and it's defective, or machine B and it's defective, or machine C and it's defective. And technically, when I do and probabilities, that's our multiplication rule. The probability of event A times the probability of event B given event A occurred. Plus, because we have or, the same thing for these. B times defective given you know you got it from B, and so forth. The nice thing is I didn't need to write out all of this because when you have the tree diagram, this conditional probability that I keep multiplying by gets taken care of already. I'm just going to go down those branches. So 60% times 10%, that takes me down the branch that ends here in defectiveness, plus 30% times 30%, again, next branch of defectiveness, and finally 10%, oops, that's not a pen, there we go, finally 10% times 40% for that branch. So I'm going to sum those products, 0.6 times 0.09 times 0.04. I said 0.6, 0.06. You should get 0.19 for the probability of getting a part that's defective. Part B says, if the part is inspected and found to be defective, what's the probability that it was produced at machine B? So this means I'm finding the probability of event B given I already know it's defective. And I've mentioned before, you can't work right to left on these tree diagrams, so we're going to have to use our formula. The formula for a conditional probability says to find the probability of both events occurring, B and defective, and divide by the conditional event occurring, the probability that it's defective. So I already know B and defective. We found that earlier. That's the 60% times the 10%, that first branch. And on part A, I found the probability that it was defective. So I just want the quotient of these two things. Oh, B and defective. I can read. I did A and defective. This is the one we want. The 0.3 times 0.3. So I'm going to take 0.09 divided by 0.19, and I get about 0.474, I believe.